Hey guys, so in this video, our problem statement is in ray tracing, how do we do MIP level selection? What do I mean by that? We have these MIP levels. This is the most detailed MIP, and then as we go down, usually app generates these MIP levels, and in the shader we need to select which MIP we need to use based on the screen distance of the object from the screen and many other factors. So let me just show you what I observed when I did not use MIP levels because my initial implementation didn't use MIP levels. So this is the oak tree, and we have the leaves. Just keep a look at the bark as I keep moving the camera closer. We see all this noise, right? This shiny shimmering effect. So for this, I'm using the most detailed MIP even if the object is far away from the screen. So that violates some Nyquist-Shannon sampling theorem, which says that uh, noise is present if we don't do enough sampling. And MIPS are one way of reducing this noise because they are pre-filtered versions of the most detailed MIP. So this is the noise which you want to avoid. So in DX12, there's no way, there's no API for us to automatically generate MIPS. We need to write our own compute shaders and generate MIP levels. So that is the reason I put it off a bit. But then when I observed these artifacts, I knew I could no longer put this off, and I took one day to integrate all to generate the MIPS and integrate into the code. So the sample which we are seeing here is hello world, which means this is a rasterization pipeline. In rasterization pipeline, it's pretty simple to select the MIP levels. So while creating the resource, I told that we have generated the full MIP chain, and I'm binding the entire MIP chain. So going to the HLSL code, if you see here, this is the texture. This is the HLSL code for the VS main and the PS main. So in the pixel shader, I'm using sample level, and I'm sampling the most detailed MIP here. So instead of doing that, we can ask the rasterizer to select the correct MIP just by doing this. So we use sample and we don't provide the MIP level. So what happens? The rasterizer will automatically select the most detailed MIP, and all the shining shimmering thing is gone. And as I keep moving, you know the most detailed MIP is used here, and if I'm far, the lower MIP levels are used. Now, the problem is, let's switch to ray tracing. And let me open the shader also. So this is the ray tracing shader. So in the closest hit shader, I am using sample level to select the highest. Right now, I'm selecting the highest MIP. So yeah, I selected the active project as ray tracing, and let's see. So yeah, since I'm using the highest MIP level, we can see all the shimmering and all the noise in the bark. So let's see if I can use the same thing as rasterizer. So let me build it, and immediately we see that we can't do that because HLSL complains that the sample is not valid if we are using lib 6.6 in the closest hit shader. So why is that? So when we have a rasterizer, the rasterizer knows everything about the screen space, the texture width, and you know, and when it rasterizes the pixels, it does it in a 2 cross 2 grid, and the rasterizer knows that if the 2 cross 2 pixels are very close, it has to select the lower MIP levels, and as they keep becoming bigger, that means they're moving closer to the screen, so the triangles are bigger and bigger. So we need to select more, we need to start selecting more detailed map. Now, as we know in ray tracing, so here, if we go to the compute cube and select one of the draw, we see that, in the pipeline state we have VSPS, and in between we have a rasterizer state, which I program in the pipeline state. There's a rasterizer here. But in ray tracing, there's no rasterizer. So all the MIP level selection needs to be done in the shader. And the Raycon approach which I took works something like this. So yeah, as we said, there's no rasterizer, so all calculations need to done in the shader. So this is a point where we shoot the ray, and the blue color shows the ray, and we need to think a little bit differently. We need to this ray is we can't think of this ray as one infinitesimal small ray which we are shooting from the screen space, but it actually becomes a ray cone. I drew half the cone here. So as you see, if it is closer, the ray cone radius is very small, and as we keep going farther, the ray the ray cone radius increases. So imagine this as a ray. I should have drawn the other half also, but this is what happens as the cone radius keeps increasing as we go further from the as the object is far and far away from the in the scene. So using this theorem in the closest hit shader, we need to do sample level, and as we saw earlier, we can't we have to give our MIP level. So I need to give the MIP level. And how do we calculate the MIP level? Is the ray code footprint. So this is the footprint we need to calculate. So that's a bit of a code. It took me a lot of research and then debugging to get it right. So here this ray T current gives is the object here or the object here. It gives the distance the ray had to travel to hit the object. And this is the theta is here, and so the tan theta meaning uh, so tan theta meaning opposite by adjacent, right? So opposite by adjacent, we are trying to calculate this bit, right? So this is uh, tan theta. I made it so explicit because I wanted to debug in the shader and see all the values. So this I'm just getting tan theta, and this I'm multiplying with the ray hit t. You We would actually think it is sine theta, but because this is the ray hit t, but apparently I think it's a close approximation to use tan theta because this is a cone and the sine theta doesn't work very well. But I found that both yield similar results. And then yeah, so then we need to it also depends on the screen resolution, because if you have a very high screen resolution, we need to use higher MIP levels even if the object is farther than if you have a lower resolution screen. So there's something called as the world space area, uh, uh, single pixel covers. and then we need to calculate. It also depends on how the UV changes on the surface on the surface of the ray. So as we move a little bit distance in the position, how much does the UV changes? So we need to calculate. So all these calculations are to get the UV density, so to say. And then putting everything together, we get the ray footprint, and we calculate a final value based on the textures width and the original textures width and height, and we return a representative value of the MIP level, and from the MIP level and from the representative value we get the actual MIP level. So if I plug everything in, even in ray tracing, I get the correct MIPs. We can do one additional thing here, that is, since we have the MIP level, we can actually say the payload color is the MIP level. So we can kind of see which MIP level is being selected. So when we are far away from from the tree, that it is red, meaning the highest MIP, 0 is most detailed and 11 is highest. And as we keep getting closer, 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 we see that we are choosing the lower, 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 lower MIP levels, which is 0 now. Now we are at 0. So this is some interesting things we can do if we calculate the MIP levels ourselves in the shader, just visualizing them. But anyway, so if we put plug in 0 here, we see that we see that all that noise when only sampling the most detailed MIP, even if the object is very far away, and otherwise we see no noise by if we select the correct MIP based on the object distance. So yeah, all the noise is gone, I guess. Yeah. So yeah, this is about it. I mean, we need so many calculations, and even before calling this, I had to even bind the position VBs here. So we get the position VBs, the UVs, and then calculate the pixel density based on with this. As we saw the pixel calculate the pixel density, and then all this is for the interpolation to get the UV after we get the MIP level, and then sampling. Ray tracing, yeah, it exposes it since the hardware itself, block itself is absent. We need to do all the calculations which were previously happening inside the rasterizer in the shader. And yeah, this is a basic approach, and let's see if I find any more artifacts. I'll keep improving this. So this is about it. Thanks for watching.